NeurIPS 2024, it's starting today. I am not in Vancouver where NeurIPS is taking place. So I want to start a series. Instead of discussing presentations and papers on the spot, I will just do it from here. I will still go through the schedule and pick some of the most interesting presentations and papers and discuss them because, like last year, the exercise of discussing these papers is interesting because I think this is an important milestone. And for the reason why we're not going there, I just want to mention this as a tangent. A little bit of a bazaar, so it's more show, and while there's still a lot of substance, I think just going there and showing up and attending all the events, it's fun, it's good, it's for networking and things along those lines. Now, we at Orange Capital Partners, we're really more interested in the substance. The purpose for us is to go there and try to understand where the science is and what could be the next interesting developments around the corner that really impact our portfolio. And that would be particularly ideas along the lines of maybe how generative models can help robotics, how robotics and systems can be improved, how AI can improve systems, how systems can improve AI. Those are the kinds of things that we're interested in, given our portfolio. Here at Orange Capital Partners, we're interested in wealth generation. The purpose of Orange Capital Partners is to generate wealth by investing in fundamentally new concepts and engineering practices. So the goal is to see around the corner, to understand where science is going, and to find the Venn diagram between science, technology, and entrepreneurship that can actually transfer knowledge into wealth. This is the goal. We're going to start discussing papers. The first paper is a paper that is in line with what we just discussed. It's about systems. It's about making systems more efficient. A diagrammatic approach towards IO awareness, or in other words, a more visual approach to the concept of flash attention. Flash attention is an idea that came out of Stanford around Chris Ree and his students. And the idea is really to exploit parallelism in deep learning. What does that mean? Well, if you have a certain data stream that goes in and then gets computed and gets output, you can do that in parallel ways. And this is why NVIDIA is so powerful. And this is, in general, why we have been able to create these gigantic models. It's because we are able to do a lot of parallel compute. Now, parallelism means a lot of things to different types of scientists. And what flash attention is doing in general, and this paper in particular, is trying to assess what kind of parallelisms can be exploited given the task at hand. So, for example, there is the parallelism of a matrix multiplication. A matrix multiplication, the actual mechanics, the math of a matrix multiplication allow for parallel execution of tasks at the same time. The reason this is important is, in particular, because of what's called the memory wall. The memory wall is the idea that we have very strong compute, but we don't have enough memory to manage the amount of compute that is being done on chip, and therefore there has to be a lot of I/O, input, output, so you have to move data around to do the compute. And the memory wall is also a metaphor for energy consumption, because you have a lot of energy consumption when data is moved. There's two problems. One is energy consumption. The other is also speed. You can have a very fast arithmetic logic unit, in other words, where actually the math happens on chip, but the thing has to wait for data to be computed. And according to studies by Google and others, more than 50% of the time of computation is actually idle because data has to be moved. So because of these two problems, energy and efficiency, people like Chris Ree and others, and a big community push is being made to try to understand the intricate mechanics of the actual workloads and parallelize as much as we can. Now, before we go there, the paper talks about the diagrammatic approach. And what this contribution is, it's less conceptual and more visual. So they visualize in a diagrammatic way what is actually going on in the processor. So in other words, like we have, let's say, a certain amount of data, and then there's a function applied to the data to transform the data, and then there's a certain output. And that can be compartmentalized, so you have a better view on what is actually going on. And once you have a better view of what's actually going on, you can then parallelize the processes. And I think the holy grail of this exercise is, of course, if you could learn how to parallelize it given the data. So in other words, we have this dynamic system that is IO aware and understands, okay, like this is the kind of data that's coming in and this is the kind of process that I'm supposed to do. Well, given that, how about I parallelize maybe more serially, or I parallelize along the model, or I parallelize them along the stream, or I even parallelize the streams themselves. So there's a lot of different parallelisms. And Jensen was talking about this last year at GTC. So this is maybe 1 or 2 years old type stuff, but now it's becoming more industrialized. And I think that's what's so interesting. And and that's what caught our attention in this paper is that we are taking an idea that grew out of Stanford. Chris Ree talked about it last year at Europe's at the keynote. It comes out of signal processing, really. What is signal processing? Well, signal processing, in a nutshell, is a similar problem. Like a signal comes in and it needs to be processed, and then it needs to be output. And the one thing you want is you don't want to do too much math on the signal. You want to do as little math as possible without losing the signal. And this is very similar to what's going on in AI, right? You want to do as little as possible with the data, but you don't want to lose information. So this is the key. So therefore, AI is kind of like signal processing. And this idea that came out of electrical engineering and signal processing now is proliferating into AI. And I think it's really powerful because it shows how interdisciplinary approaches can work. It also shows that in a nutshell, maybe everything is actually only one big problem, which is how do we take an initial condition and we transform it into something else. You could look at it two ways. So one way to look at it is it's all just one big problem, signal processing, and the other is it's really interesting how different disciplines can contribute to the problem. Regardless of how you look at it, I think what's really powerful about this is the concept of applying known concepts of signal processing to a new problem, which is AI and neural networks, and have an IO there. So again, that means that we take information coming in and we adjust the parallelism that is acquired to have the most efficient compute. And I think this is really important for, let's say, for us. We have a very large position in NVIDIA. And when we think about these types of problems, we can look at it, of course, always two ways. One way is we can say, well, this will kill NVIDIA. But the other way to look at it is also, well, maybe this is what makes NVIDIA so strong. According to the chief science officer of NVIDIA, his name eludes me right now, the NVIDIA has been able to grow much, much faster than Moore's law when it comes to compute and performance. And in a nutshell, what we're most interested in as users and investors is not compute, it's not flops, it's not any of those things. It is tokens per dollar, or actually solutions per dollar. So how much do I have to invest to get stuff done? And this type of work, this FlashAttention and this diagrammatic approach towards IO-aware hardware is a big, big step towards lowering the cost per token. If you will, token is just a metaphor for actual solution because the tokenization of models helps solve problems. And what we're most interested in is help, dollars per solution per dollar. So have more solutions per dollar or less dollars per solution. So to summarize this paper, IO-aware hardware for deep learning, it's a really good example of how the community is coalescing around a really interesting idea. The idea being that we use signal processing concepts in deep learning with the goal to reduce the memory requirements per compute So we want to parallelize as much as we can the workflows so we can keep the data on chip memory while the computation is done. We can do that by either parallelizing as much as we can or quantizing. Both methods are being used. But what's most interesting in this particular paper is also the idea or the approach, the possibility that we could have a learning approach towards parallelization. So in other words, we could have, like the title says, IO-aware hardware. Whatever comes in, we adjust the parallelism of the system towards the most efficient execution of the task. And maybe finally also what that means, of course, is for people like NVIDIA in particular, is that you want to have a software layer on top of your hardware that allows for this type of flexibility, that allows for algorithms that help execute other algorithms more efficiently. And I think this is a really exciting sort of compound way application of AI, where we use AI to make other AI workflows more efficient. Thank you.